Good evening, everyone.
Good
Good
evening.
evening, sir.
Good evening. Good evening. I hope you can all hear me. Sorry for the delay. There was like some technical issues with the setup. Now everything is fixed and we can start the lecture. And the objective of this lecture is to particularly cover the climate science part that is mentioned in your GATE syllabus. It will also be important for your NET exam as well, because their climatology and atmospheric sciences is also something that is asked, also oceanography. So we will not go into as much detail as, let's say, you would expect from in net exam, but the main objective is for GATE exam, and also for you all to understand a bit about climate change, because superficially we do understand climate change, also the principles behind it, but if you start to go a little bit deeper, you see like it is way more complex than kind of like the stuff that we learn in school. Okay, so this is what we'll start first of all. Okay, so the first thing that we should look at, okay, before like studying, doing any climate change analysis, what do you think is the thing is should look at first of all the thing like, is changing earth climate something that is unexpected? Okay, so first of all, it is actually not whether the climate is changing or not, the rate at which climate is changing and what is the cause of that climate change, that is important. Throughout the earth's history, ever since earth came into existence 4.6 billion years ago, its climate has never been constant. The climate of the earth is always changing. Okay, the important thing is the rate of the change. Okay, uh, effect of that change. Okay, so for example, humans were not present on earth for vast majority of time. Okay, how will this climate change affect humans? Those things are important, and also the rate of the change. But if you look at like not so distant past, okay, ever since like mammals became more abundant on earth after, let's say, the Cretaceous mass extinction, let's go back to early Eocene, or even you can go to Paleocene. Okay, so at the boundary of Paleocene Eocene, you had what is called the PETM. Do you know what does PETM stand for?
Paleocene, Eocene, thermal maximum.
Okay, at that time the temperatures were approximately 15 degrees hotter than what we see today. Okay, the average temperatures were 15 degrees Celsius. This is quite hot. Okay, if you look at the current temperatures, okay, so where we are currently somewhere over here. Okay, so if you take a little bit of a historical context, okay, so we are somewhere over here. Okay, 0 I think represents the pre-industrial average, so that is your current temperature. So for majority of the past we have been much hotter than the current temperature. Okay, but if you look at the recent past, more recent past, so the scales are not the same. Here it is 10 million years, then it is to 1 million years, and here it is only 100,000 years. Okay, the splitting. So you can see in more recent past, actually we have been on the colder side than what we see present. Like we did have these interglacial periods. So what you see here are basically when temperatures are high, that those are the interglacials, and when the temperatures are low, those are the glacial periods. Okay, so these are basically cycles of ice ages that have been happening for several past hundred thousands of years. Okay, and our CO2 concentrations have also been pretty low through this time. So in Paleocene, Eocene thermal maximum, the CO2 concentrations were close to 2000 parts per million. Okay, currently we are at just above 400 parts per million. Okay, so the present value is somewhere over here. Okay, so just above 400. So you can see here, like even for much of the history, our CO2 concentrations have been much higher than the present also. But again, if you come to the more recent past, the CO2 concentrations were much lower. They were hovering around, like you can say, in between 180 or 200 to 300 parts per million, ppm. Okay, and overall, like when you are kind of like in this stage, CO2 is actually a gas which is life supporting. Okay, so life is not possible, will not be possible on Earth as we see today without CO2. It is food for plants. It keeps the Earth warm. Greenhouse Earth would be way too cold for life. Okay, it's just like the amount of CO2 that's crucial over here. Okay, plants actually need CO2 for photosynthesis. So you can see here, and kind of like the minimum CO2 that they need in atmosphere, below which photosynthesis becomes really difficult. And then plants, basically the plants, actually, at least that those we see today, they need at least close to 150 parts per million of CO2. Okay, they need at least 150 parts per million of CO2 to support plant life. Okay, so you can see here, first of all, CO2 is quite important for supporting life. So when we study about like climate change and greenhouse effect, it's kind of like we have preconceived notions like all CO2 is polluting and it's bad. It's actually life supporting, and you need some minimum concentration in the atmosphere to support plant life. Okay, so in some of those glacial periods in the recent past, we had been like pretty close to that limit. Okay, but ever since industrial revolution, the CO2 in the atmosphere has been increasing. Okay, and especially it has been increasing quite dramatically since after 1950s. Before that, basically what happens is, like, when you release CO2, it does not all end up in the atmosphere. Some of it is reabsorbed also. Let's say it gets reabsorbed into the oceans, it dissolves into the oceans. Some of it may lead to more plant growth, so some of this gets fixed in more biomass. Okay, so those are like natural. There are some natural sinks of CO2 also. So not all CO2 that is released will end up in the atmosphere. Actually, if we make all the calculations that all the emissions that humans have made until now, only half of those have actually increased the CO2 concentration in the atmosphere. So half of them have ended up in the atmosphere. Half of them have been basically reabsorbed in some of the natural systems. But you can see over here that Earth's climate has changed quite dramatically through the past, through its history, and we are currently over here. And these are some of the IPCC. IPCC stands for Intergovernmental Panel on Climate Change. So there are different scenarios. So for example, if we don't stop greenhouse gas emissions, if they stay the same, or if we go to net zero, means we are not emitting any new net greenhouse emissions. So you can see here, overall temperature can fall back a little bit in the future because some of the excess CO2 that we have released will get absorbed with time. So CO2 will fall back with time, although it may take a long time. So we can go. So these like in the most aggressive emissions. So these are models, these are future predictions. So there is always uncertainty in those. So you cannot take them always at the face value, but we can go up to as much as 10 degrees Celsius warmer. Okay, so to understand that, first of all, if you look at the most recent past, okay, at least for 2000 years. So again, this is from the Intergovernmental Panel on Climate Change assessment report, okay, of working group 1. You can see here, like if you take data for the past 2000 years, and you can see here, compared to the pre-industrial average, Earth was a little bit warmer in the medieval period. Okay, so roughly 0.25 degrees Celsius warmer. And then there was what is called a little ice age, which ended in 1850, and ever since the temperatures have been increasing. Somewhere around here, the greenhouse gas emissions basically started increasing in the atmosphere, and then this increase is attributed to basically those greenhouse gas emissions, this increase in temperature. One thing to note is that this is the reconstructed temperature, and whereas this is from the modern day temperature record. So reconstructed temperature, for example, based on tree rings. Okay, so these are not the two things which are exactly same set of data. So of course there is more uncertainty in the reconstructed record. Okay, so any doubts, any questions until this point? So we'll go through some of the basic principles now of climate change. Okay, so first of all, what happens is, like on any planet, we'll consider some hypothetical planet. If there is no greenhouse effect, what will happen is, let's say that planet, you assume it to be a black body, or although like no body is a perfect black body. So sun is emitting some radiation, and that planet is emitting some radiation. If the planet is too cold, so what will happen is incoming solar radiation will be more and it will emit less. So its temperature will start to increase. It will increase up to a point such that you are in balance. So when will you be in balance? When incoming is equal to
outgoing.
Equals to outgoing. Okay, so that is an important thing. And just 1 second. Okay, so incoming becomes equal to outgoing radiation. Okay, so now on Earth, basically what happens is, one thing which is very crucial is to know that how the surface of Earth cools. If we make these calculations, okay, at equators Earth will be too hot, and at poles it will be too cold. Okay, there is transport of basically heat energy on the, if you're talking about on the surface of Earth, it has atmosphere. Okay, so there is greenhouse effect, but also there is mixing of heat energy and redistribution of heat energy throughout the surface. Okay, so we'll study this concept of characteristic emission level a little bit later. Okay, so again, you don't need to go into math in detail. Okay, so radiative budget for again a hypothetical planet. If there was no atmosphere on the Earth, okay, if there was no atmosphere on the Earth, or let's say if there was no greenhouse effect, okay, I wouldn't say no atmosphere, no greenhouse effect. Okay, all we are trying to do is we are saying like sun is this much far away, the temperature of sun is approximately 6000 Kelvin. Okay, and it is this much distance r away from the Earth. So what is the flux reaching at Earth? Basically, what is the radiation reaching at Earth? And we take cross-sectional area of Earth, and then Earth will be emitting some radiation. And if we make this like calculation, at what temperature will there be equilibrium? Equilibrium means outgoing radiation equal to incoming radiation. The answer that we get is 255 Kelvin. How much is that in degree Celsius? Can anyone tell me? How much is that in degree Celsius?
Minus 18.
Minus 18. Very good. So Earth would be minus 18 on average. So life will not be possible without the greenhouse effect. Now again, here it is no greenhouse effect. Now in this case, basically we do assume there is atmosphere. Okay, but that atmosphere is not producing greenhouse effect, because this 0.31 is what is called the average albedo of Earth. What do you mean by albedo? What is albedo?
The amount of radiation reflected by the Earth.
Reflectivity. So on average it is about 30%. So 30% of all the radiation is reflected from the Earth, and majority of the albedo comes from clouds, tops of clouds. If you have ever traveled in a plane, you can see they're all white and they're reflecting most of the radiation back. Okay, so from top of the cloud. So you need atmosphere to get this much albedo. Okay, but we are assuming that atmosphere does not have a greenhouse effect. Okay, if we assume there is no atmosphere, okay, basically we mean like the radiation is not getting reflected, majority of it is not getting reflected. Okay, so if there is no albedo, means all the radiation is absorbed. Okay, so maybe it is Earth will still have some albedo even if it does not have atmosphere, but its albedo will be much lower. Okay, but without atmosphere the temperature will be around 272 degree or 272 Kelvin, or minus 1 degree Celsius. Okay, again assuming no albedo, which will be the case if there is no atmosphere, or not exactly the case but close to the case, because water, earth, 70% of earth is water, and water reflects very little. Okay, most of the energy that falls on water is absorbed. Okay, so this minus 18 degrees Celsius, 255 Kelvin. Okay, so this is an important figure that you should remember. So if you look at the earth, okay, what is the actual surface temperature of the earth? On average, it is 288 Kelvin, roughly 15 degrees Celsius. Okay, roughly 15 degree Celsius. So on average, earth is roughly 15 degrees Celsius or 288 Kelvin. Okay, so incoming radiation and outgoing radiation. Okay, for these to balance, temperature, what temperature do we need? A temperature of 255 Kelvin is needed, or minus 18 degrees Celsius is needed. So what is happening is earth is now at 288 Kelvin. So what does that mean? If you look at just the surface of the earth, it means at the surface, okay, so we are releasing more than what is incoming. Okay, first of all, is this clear? Because total radiation, you know, from Planck's law is proportional to T to the power 4. Okay, okay, temperature to the power 4. So if temperature is higher, radiation is higher. Okay, so first of all, if you look at just this figure, let's say if no one gives you any other information, 288 Kelvin. So what do you think? 255 Kelvin is needed to match the incoming radiation on the surface. Okay, 288 Kelvin is the surface temperature of the earth. So earth is kind of like, you can think of it as emitting more than it is getting. Okay, so where do you think will equilibrium? What happens to temperature as altitude increases?
Decreases.
Okay, so you think of this like you have this 288 Kelvin. So if you go slightly higher up, okay, let's say you go to a slightly higher up level. So temperature will decrease if you keep going higher and higher. At some point it will become 255 Kelvin. Okay, so at 255 Kelvin, the incoming radiation will be equal to outgoing radiation. Okay, so incoming radiation will be equal to outgoing radiation. That level is called the characteristic emission level. Which is, you can think, roughly 5 kilometer. That is, it is within troposphere. Okay, is this clear, everyone? First of all,
Yes, sir.
okay, we'll go in a little bit. We'll discuss about this a little bit more later also. Okay, so basically what happens is, you have this surface as 288 Kelvin. Okay, and that is the character. So we're just defining the characteristic emission level. Now this is a picture of Earth's radiation budget. You may have seen it many times in the past also. Okay, when you study different cycles, radiation budget. So total incoming radiation is 340 watt per meter square. Okay, roughly we're talking about that much. And the surface only receives actually I'm not talking about the whole earth. On average, the surface receives only 163 watt per meter square. Some of it is absorbed basically, some of it is reflected directly by the clouds. Okay, as I said, like roughly 30% of it is reflected, and also atmosphere absorbs some part of it. Okay, and total reflected is roughly 9900, so that becomes 1/3. Okay, because some of it is reflected by surface also. Okay, now this is not I would say very this one is okay. Okay, some of these diagrams that you will see, they are not very good, in the sense that many of them will ignore this part. Okay, so the surface of earth, okay, it cools primarily by what we call convection, okay, in atmosphere. So what happens is, the surface of the earth, you can see here, it is trying to emit radiation, but a lot of that radiation is coming back also. So you have these what is called the greenhouse gases. So for example, these greenhouse gases which are present in the atmosphere, what they do is, okay, I'm drawing those as stars. Those greenhouse gases will emit this, will absorb this radiation. Okay, in fact, very near the surface. So what happens is, your atmosphere gets denser, okay, as you are closer to the earth surface. Okay, here the atmosphere is rare, okay, or less dense. Okay, so if you look at like close to the surface, okay, all that radiation that is trying to escape, okay, so the atmosphere is practically opaque. Okay, it is practically opaque to infrared radiation which earth is emitting. What do you mean by practically opaque? What do you mean by opaque? It means that most of the radiation is absorbed. It is not able to pass. Okay, you can think of it as like glass is transparent, light can pass through it. If you have a wall, light cannot pass through wall, brick wall, let's say. Okay, so that brick wall is opaque. So radiation cannot actually pass through the atmosphere. Okay, so it does not radiate very efficiently from near the surface. Okay, but what happens is, as you go up, okay, what happens to atmosphere? Atmosphere is less dense. Okay, atmosphere is less dense, and over here, let's say at some height, okay, the radiation can escape earth. Okay, atmosphere no longer opaque. Okay, radiation can escape. Okay, and what we are trying to do here is, we are trying to basically technically understand the greenhouse effect. Okay, in school you just learn that this carbon dioxide is present. Sometimes people will say it is kind of like a blanket, or it allows radiation to come in but does not let it go out. Okay, those are like very superficial discussions. Okay, what actually happens on earth is, earth has atmosphere. There is turbulence, there is mixing of gases. Radiation is not the only way of heat transfer. What are the ways of heat transfer? What are different ways in which heat transfer occurs?
Conduction, convection, radiation.
And sometimes advection is also there. Okay, so if you are talking about Earth and space, yes, Earth will have to cool by radiation, but inside the Earth, okay, conduction and convection are also important. Okay, so what happens is, in this part of the atmosphere, okay, there is what is called turbulence. Okay, so you see, for example, thunderstorms, thunder clouds, warm air rises up, it condenses, produces clouds, condensation releases heat. Okay, when the ground, there is water on the ground, when water is evaporating, okay, it is absorbing heat. Okay, so it is these processes actually which are cooling the surface of the Earth. Okay, it is not radiation. And actual greenhouse, like the name greenhouse effect comes from greenhouse. Okay, what is a greenhouse? Man-made greenhouse, I hope you all know that. Does anyone know what is a man-made greenhouse?
In the garden,
Yes.
used in the garden. Used in the garden, like the
Yes.
green color.
Yes, basically, what is there is a, let's say people say, a glass sheet around it. Okay, so what happens is that it allows incoming radiation. Okay, and the glass does not allow the emitted radiation to go back. Why? Because the incoming radiation, first of all, we'll see that part also. Incoming radiation has higher frequency, lower wavelengths. Outgoing radiation has lower frequency, higher wavelength. So these gases, for example, carbon dioxide and all, they block that what is called long wave radiation. They don't block short wave radiation. But in actual greenhouses, which we use to grow vegetables and all, or let's say if you put your car, okay, on a sunny day outside, it gets very, very hot inside. Okay, and many people believe that the main reason is that glass does not allow the emitted radiation to go back. That is not true. Glass is actually transparent to emitted radiation also. The main reason is inside the car, there is no convection that is taking place. There is no air that is blowing inside which can cool the surface. Okay, so the air inside stays inside. Okay, so this process is not taking place inside. So Earth's surface basically cools by this overall, you see this turbulence mixing of the atmosphere. Okay, now this turbulent air gets warm, okay, as it is near the surface, then it can rise up. Okay, it can rise up, and then it can rise up even beyond that also. It is not that it will rise up only to that point. Okay, when it rises up above this characteristic emission level, okay, or where the concentration of atmosphere or the density of atmosphere is not enough, so those let's say greenhouse gases are less. So for example, here you can see these greenhouse gases. There will be a lot of greenhouse gases because atmosphere is dense over here, and it gets less dense as you go up, higher up. Now those greenhouse gases which were blocking the radiation, they are present in less concentration, and then your radiation can escape. Okay, now radiation can escape. Okay, is this clear, everyone?
Yes, sir.
Okay, so now what are these greenhouse gases? Okay, so first of all, which is the most important greenhouse gas on Earth?
Carbon dioxide.
Anyone else?
H2O, sir.
H2O, water vapor. Okay, so the most important greenhouse, the most efficient greenhouse gas that is present on Earth is water vapor. Okay, carbon dioxide is important, but not as important as water vapor. Okay, just the presence of water vapor in the atmosphere, it contributes 50% to the greenhouse effect. Okay, and if you include clouds along with it, clouds also play a very, very important role. Okay, if you have ever seen, like, usually cloudy nights are not very cold. Okay, because the clouds trap the heat. Okay, kind of like they do not let the heat escape from the surface. Okay, so together they contribute roughly 70-75% of the greenhouse effect. Okay, water vapor and cloud. So water alone contributes almost 75% to the greenhouse effect. Now these are not anthropogenic. Okay, carbon dioxide is emitted by humans, so it is anthropogenic. It will be considered anthropogenic. although like human activities affect water cycle as well, it's not like they don't, but carbon dioxide contributes less than 20% to the overall greenhouse effect. And then there are other gases also, such as ozone, nitrous oxides, etc., etc., which also contribute to the greenhouse effect of the earth. Okay, so why does this greenhouse gas effect occur? Okay, so first of all, if you, where have you seen this diagram previously? In remote sensing.
Remote sensing.
Atmospheric windows, right? So what do you
Yes,
see?
sir.
Yes. So what do you see over here is that, first of all, this is the solar radiation. Okay, solar radiation has lower wavelength. It is in the visible spectrum, majority of it. Okay, the peak here is in visible spectrum. Some of the incoming solar radiation is getting absorbed. You can see here it is not coming. Some of it will be reflected. Okay, ozone is absorbing the UV radiation on this side. Okay, so overall your solar radiation emitted by the sun is this, or which should come at the top of the atmosphere. Okay, but on the surface only 70% of it will come. Okay, or so only 70% of this is absorbed, rest is reflected back. Okay, and what you see is earth over here emits, okay, in the infrared region. Okay, because it is at colder temperature. Okay, so you remember lambda max is inversely proportional to temperature. Okay, so if you increase temperature, your lambda max decreases. So sun is hotter, so your lambda max means value of wavelength at which you get maximum intensity is decreasing. So which law is this one? We have covered in remote sensing. Which law is this one?
Planck's law.
No, Wien's displacement law. Okay, so it is Wien's displacement law is that as temperature increases, the wavelength at which maximum radiation is emitted, that wavelength decreases. Okay, so earth is emitting at longer wavelengths in the infrared region. Now the main gases that you see in atmosphere, okay, so what is happening over here in this figure is everything that you see white is transmitted and everything that is in gray is absorbed. So you can see here just by looking at the figure that which is the most radiation absorbing gas in the atmosphere, just based on this figure.
Water vapor.
Water vapor. Okay, then you have after that carbon dioxide. Okay, so carbon dioxide, so you can see here water starts to emit in this part, but carbon dioxide is now absorbing over here. This whole part is absorbed by water. Now water has a window over here, but then you get carbon dioxide which absorbs over here. This carbon dioxide peak is not very relevant, this absorption by carbon dioxide, because water is already absorbing over here. Similarly, this one is less important. So, and then there is some absorption by other gases as well, which is very, very minor. Okay, do you understand this figure first of all? Okay, so now if you add these up together, okay, so this is, add all these up together, this is the figure for total atmosphere that you get. Now you can see here for the incoming radiation, you can see there is some absorption of the incoming radiation here as well. So that is why you see some absorption over here. Okay, this part is not, everything that you see over here in white is not coming. Okay, so what is happening is a lot of it is passed. Okay, so the radiation that is coming from the sun is passed, but if you see a lot of radiation that the earth is emitting, okay, most of it is blocked. So some of it is passed, of course, but most of it is blocked or absorbed, let's say, by greenhouse gases. Okay, so near the surface a lot of radiation is absorbed, that is why I say like it's almost opaque near the surface. When you go, okay, a little bit higher, okay, above into the atmosphere, where the atmosphere is thin, then the greenhouse gases can basically they are not present in sufficient quantity to block all the radiation, and radiation can efficiently escape. Okay, so overall you see the total radiation that is coming from the sun was 394 watt. These values are important, at least sometimes they can ask you those values also, how much radiation is coming on earth. Okay, 30% was reflected roughly. Okay, so you are left with 307 watt per meter square. Okay, so 307 watt per meter square is the one that is coming. Now a lot of it is being absorbed. Okay, so now this gray curve also represents what is basically this now, and this is basically organized with what we say frequency, not wavelength. Okay, now what is the greenhouse gas? One thing to note is that overall this red one versus black area, okay, these are the ones which are telling you what is going back into the, what is being radiated back into the let's say what is being radiated back into the space. Okay, overall effect of doubling CO2. Okay, if we double the concentration of CO2, so what was pre-industrial CO2 concentration?
0.03.
0.03 was like, no, that concentration, what is the units? 0.03. It was around approximately 280 parts per million. Okay, current, I don't know the exact figure, maybe approximately 410 ppm. So if we double CO2, how much will it be?
$560.
Okay, so effect of doubling the CO2 is 3 watt per meter square. Okay, out of this like total budget that we are seeing, 3 watt per meter square. Okay, basically more energy absorbed. Watt per meter square more energy absorbed by doubling of CO2. Okay, another important thing is the effect of adding CO2 is logarithmic. What do you mean by logarithmic? Means, okay, to produce the same effect, you'll have to double the CO2. Okay, so for example, you go from 280 to 550. Okay, current is, we have not yet doubled the CO2, is at 410. Okay, and then what will be double of that? What will be double of 550 or 560?
1100.
Let's say you said like 560 over here. Okay, and then after that, okay, so it is basically this changes the radiation budget by 3 plus 3 watt per meter square. Now you'll have to add a lot of CO2 after that to produce the same effect. And then again plus 3 watt per meter square. Okay, so after a while, basically the warming potential of CO2 decreases if you're talking just about CO2 if you add more and more of it. Okay, it is kind of like it is, as we said, like close to the surface, the atmosphere is already pretty opaque. Okay, so it is not already transmitting much of the radiation, so adding CO2 does not produce that much of an effect. Okay, And again, this is just by CO2 adding. Okay. Now greenhouse effect. Okay, this is another way of thinking of greenhouse, which is actually the correct way of thinking of greenhouse effect. Okay. So we said like there was characteristic emission level. Okay. So what was the characteristic emission level? What should be the temperature? How many kelvins?
255.
Okay. Now what will happen is if you add, let's say, greenhouse effect, more carbon dioxide to the atmosphere, what will happen? Let's say initially Earth was emitting radiation at, as I said, like it gets, when you go higher and higher up above the surface, okay, at some level the concentration of greenhouse gases decreases. So there are a lot of greenhouse gases. Okay, and higher up the concentration decreases so that at certain level they may escape. Okay, now if you add, let's say over here, it can escape. Now let's say if you add more CO2 to the whole system, okay, additional CO2, let me draw that in purple. If you add more CO2 to the whole system, what will happen to this level from which radiation can escape? Will it increase or will it decrease?
Down.
Will it move up or down?
Move up. Down.
Why down? It will move up because if you are down, the concentration of greenhouse gases is very high, radiation cannot escape. Now if you add more CO2 to the whole system, everywhere there is more greenhouse gases, okay, so it will rise up a little bit. Okay, so it will rise up. Okay, because now there are more greenhouse gases, you have to go further up to find less concentration. Okay, now what happens? Okay, there is what is called a lapse rate. Do you know what is lapse rate?
So temperature decreases with height.
With altitude, right? Do you know what is its value?
6.5 degrees Celsius per kilometer.
Okay, so this is what is drawn over here. Okay, roughly 6.5 degrees Celsius per kilometer. So let's say here we said like on average it was 288 Kelvin roughly. Okay, so at some characteristics, so we said like Earth should be emitting at 255 Kelvin. That is where the radiative balance is present. Okay, now because you have added greenhouse gases to the system, okay, initially let's say the radiation was being emitted, there was equilibrium at some height. Okay, at some height there was equilibrium. Okay, so ultimately what if the surface of the temperatures, the temperature of the surface of the Earth will be determined. So equilibrium will determine the temperature at this characteristic emission level. Okay, so you think of that, higher up in the atmosphere there is some level where radiation can escape. Temperature of that level should be 255 Kelvin. Temperature of that level should be 255 Kelvin. Okay, so where radiation can escape, okay, that is where radiative balance will be present. If radiation cannot escape, there is no radiative balance. At that case, some other processes have to be present to cool the Earth. But where radiation can escape, that incoming should be equal to outgoing. That is where we decide it. Okay, so now if you raise that radiative, okay, if you raise that characteristic emission level, okay, so now you are no longer at 250. You see your temperature has gone below 255 Kelvin. If you add greenhouse gases, they cannot escape from here. Okay, they will escape at a higher altitude, but at a higher altitude temperature is not 255 Kelvin. Okay, so the temperature must again go back to 255 Kelvin. Okay, because equilibrium should be attained. And when you have to attain equilibrium, you go to this level over here. Okay, everything has to warm up below it. because you have to follow that lapse rate also, which is 6.5 degrees Celsius per kilometer. This is the real greenhouse effect. Okay, it is this combination of all these things. Okay, the atmosphere, the lapse rate, that it is there is convection within the atmosphere, that is the primary cooling method. Okay, do you understand this? I can explain once more if you don't understand any part of it. Okay, so basically what we are saying is there is balance when the temperature is 255 Kelvin. Okay, somewhere in the atmosphere. Okay, and somewhere in the atmosphere there is a level as you move higher and higher in atmosphere from which radiation can escape. Okay, the cooling mechanism below that level, because radiation cannot escape, has to be convection. Okay, you see all those weather phenomena, that is what is redistributing heat on earth. So as you heat the ground surface, okay, air gets warm, that air rises up. Okay, it carries heat with it. There is water present in plants, there is water present on the ocean, that is evaporating. Evaporating water, okay, also takes up heat. So it is evaporation, transpiration and convection which is most like which are basically cooling the surface of the earth. Now as that air rises up, okay, it becomes less dense. Okay, it becomes less dense, and that at certain level it can emit the radiation because concentration of greenhouse gases is less. That level at which its temperature is 255 Kelvin is called characteristic emission level. Basically the temperature at which radiation can escape, the temperature there should be 255 Kelvin. Okay, now if you raise that level up, okay, so temperature here should be 255 Kelvin. Now if you start increasing temperature from this point by 6.5 degrees Celsius, you will find that the surface has become warmer. Do you all understand the greenhouse effect?
Yes, sir.
Okay. Now the thing is, there is a concept which is called climate sensitivity. Which is the effect of doubling CO2 on mean earth temperature. Okay, so doubling CO2, if you double the CO2 concentration, what will be, how much will the earth's surface temperature change? Okay, so just for CO2, okay, okay, if we consider the effect of just CO2, okay, doubling CO2 will produce roughly 3 watt per meter square of additional radiation absorption, which will produce a temperature increase of roughly 1 degree Celsius. Okay, it is not a huge temperature increase. Okay, and then you will have to, so with all the emissions that we have been doing for several hundreds of years, we have only increased from 280 to 410. Okay, now further adding CO2 will be less and less efficient in warming. Okay, so if you double CO2, it will be 560 to 560, it will produce a effect of 1 degree Celsius. Now again the key word over here is just CO2. Okay, that is, we assume what is called no feedbacks. Okay, so now there is a concept of what is called a atmospheric feedback. Okay, so a feedback is, let's say you have a system. Okay, you disturb that system by some change. Okay, that some change could be, for example, increased forcing, radiative forcing. Suppose we double the CO2, okay, we double the CO2 concentration and the system is disturbed, okay. So the system is disturbed by doubling CO2. So it introduces another plus 3 watt per meter squares of radiation into the system. So the system responds, okay. So let's say plus 3 watt per meter square. Okay. The system responds by some change. Okay, so your temperature increases, let's say by 1 degree Celsius because of this. Now on Earth, if you increase its temperature, that temperature increase itself will produce certain changes. Okay, so this temperature increase, okay, introduce changes. Okay. Which is called feedback. Okay, so you disturb the system changes, okay, and that further basically affects the system, okay. So and then this feedback loop occurs, okay. So I will give you one example, okay. The most important feedback in all climate systems is what is called the water vapor feedback. Okay, what is the most important feedback is water vapor feedback. Okay, so let's say you have warm air versus cold air. Which of these can hold more water vapor?
Warm air.
Warm air can hold more water vapor. Again, assuming constant relative humidity. Okay, so let's say relative humidity must be on average 50%. Okay, so that 50%, because warm air can hold more water. Okay, so overall so what will happen now? This change, for example, this temperature change that we are producing over here of 1 degree Celsius, it is making the earth a little bit warmer. Now warmer atmosphere will be able to hold slightly more water. Now what is water? Is water vapor a greenhouse gas?
Yes, sir.
Yes, right. So basically effect of CO2, you added CO2 to the system, it disturbed the system. Okay, let's say you disturb the system by additional 3 watt per meter square. Okay, so you have disturbed the system by this. Now earth is approximately 1 degree Celsius warmer. Now atmosphere can hold, warmer atmosphere can hold more water vapor. Okay, warmer atmosphere can hold more water vapor. Okay, so there is additional greenhouse effect. Okay, now this additional greenhouse effect, will it amplify warming or nullify warming?
Amplify.
So it can amplify warming. So it will amplify warming. Okay, so it is actually from these feedbacks, okay, that this global warming or climate change becomes more scary. Okay, per se adding CO2 itself, just if we consider the CO2 effect, its effect is that it will increase the temperature. Every doubling of CO2 will increase temperature by just 1 degree Celsius. Now, and this is where most of the uncertainty comes from the feedback. Okay, and the formula that you see here, delta T naught 1 by F. Okay, so basically the total temperature change will be, if there were no feedbacks, let's say temperature increase would have been T naught 1 minus F. Okay, so feedbacks can be positive or negative. Okay, so feedbacks can be positive or negative. Okay, so if let's say positive feedback and negative feedback. Okay, let's do some examples. Example, if F equals to, okay, let's say delta T naught is equal to 1 degree Celsius, F is equal to 0.5 plus. So what will be delta T? What will be delta T?
2 degrees Celsius.
It will be 2 degrees Celsius. Okay, so 1 minus 0.5. Okay, if F is equal to 0.8, what will be delta T?
Five.
5 degrees Celsius. Okay, if F is equal to 1, what will be delta T?
0.
Infinite.
Infinity. So you can see here this feedback factor. Okay, so most of the debate in overall climate science is on this part. What is this feedback factor? It is not on this. Okay, everyone agrees that it is like 1 degree Celsius temperature you will increase. Okay, if let's say the feedbacks were negative, negative means this feedback that is providing, instead of amplifying warming, it reduces warming. Okay, so one of the simplest feedback feedback effect is, if earth is warmer, it emits more. That is a negative feedback. Okay, so that will reduce warming. Okay, so feedbacks could be negative also. It is possible. So if F is equal to 0. Let's say minus 0.5, so what will be delta T in that case? Should be easy to calculate.
0.6.
1 divided by 1.5. So it will be 0.6. Okay, so if the feedback is negative, okay, so your temperature increase will be less than 1 degree Celsius. Okay, which would be there in presence of feedback. Okay, so this is the concept of feedbacks. So you can see here this feedback factor, if you change it a little bit, so overall effects could be really high. So what are some of the feedbacks? So for example, some of the positive feedbacks will be, first of all, snow and ice cover loss. So snow reflects more. Okay. So for example, let's say areas are more snow covered. As you increase warming, the snow cover reduces. Now snow cover reduces means less light is reflected. If you have seen snow, it is very bright and white. Okay, it reflects a lot of radiation. So whereas if it is converted to water, water absorbs more radiation than snow. Okay, so that is a positive feedback. If you, let's say, increase temperature by 1 degree Celsius, that will melt some snow. That some snow melted will lead to more absorption. Okay, which will lead to further increase in temperature. So it is a positive feedback. Water vapor we have already seen, which is the most important feedback. Okay. Okay, melting permafrost releases methane. Okay, permafrost basically it is the soil which is permanently frozen and a lot of methane is captured into that soil. So if that is melted, that methane will be released into the atmosphere, which will produce further warming. Okay. Negative feedbacks: warmed earth radiates more. Okay, plants remove carbon dioxide from air. Okay, typically as you increase carbon dioxide in the atmosphere, plant growth becomes more vigorous. Okay, so plant growth plants are like, they do best around like more than like 1000 parts per million of carbon dioxide. Some oceans remove carbon dioxide from the air. Other feedbacks which we are uncertain of. Okay, biggest uncertainties: which you don't know about are basically cloud feedback. Okay, so clouds are interesting because clouds, they reflect radiation, but they also provide greenhouse effect. Okay, so the tops of the clouds, the radiation that is coming is reflected from the top, but the radiation which is below the clouds, that is trapped by the clouds. Okay, so overall, if you increase by 1 degree Celsius, how is the cloud distribution on the earth going to change? Okay, the height at which clouds occur, will that change? How much that will change? On which latitudes do we see what percentage of clouds, etc.? How will that change? So those things are important, okay, to understand, but there is a huge uncertainty in that cloud feedback. Okay, so overall, this picture is again from IPCC, Intergovernmental Panel on Climate Change, and they have tried to estimate basically, so CO2 is just one thing, how much total radiative forcing we have produced on earth. So this is what it says. So CO2 concentration on earth has increased. So the increase that has taken place until now, so it has produced, basically disturbed the system by 1.68 watt per meter square. And again, the sign is positive in this side, negative in this side. Negative means you have reduced the radiation that is being absorbed. Okay, so some human activities have actually also reduced the absorption. Okay, so CO2, you can see here, it has increased the absorptions. Then CH4, methane, has also increased in the atmosphere, so that has added another 0.97. CH4 is much more efficient than CO2. Greenhouse gas. So even though it is present in much lower concentration, its effect is pretty significant, 0.97. Okay, and this 1.68 is not the effect of total CO2 in the atmosphere. It is additional CO2 that we have added to the atmosphere that is causing an increased radiation absorption of 1.68 watt per meter square. Okay, methane 0.97. Okay, halogens, carbon, basically ozone, etc., chlorofluorocarbons. Okay, plus 0.18, and nitrous oxide plus 0.17. Okay, so these are all your greenhouse gases. Okay, these are all your important greenhouse gases. Can you add these all up together and tell me how much radiative forcing we have increased due to greenhouse gases?
Three, sir.
It is
Three.
approximately 3 watt per meter square. Okay, so just by adding greenhouse gases, if you consider other greenhouse gases also, so we have already introduced forcing equivalent to doubling of CO2. Okay, in that time, Earth's temperature has increased by roughly, let's say, 1 degree Celsius. Okay, so it is kind of like matching what you would expect in case of no feedback. Okay, so we said like if there is no feedback, maybe it should be 0.75. There is slight positive feedback. 2023 was, I think, a little bit hotter, okay, than 1 degree Celsius. But if you look at like over a longer time period, okay, few years, roughly we have increased the greenhouse gas forcing by 3 watt per meter square, and the temperature of the earth has increased by 1 degree Celsius. Okay, 1 degree Celsius is not problematic. Okay, where is the problem coming from? It is from the feedbacks. Okay, and again those feedbacks are being predicted by models. Okay, so those feedbacks are being predicted by models, but just looking at these numbers, it is not that much of a problem. Now, why are we still predicting temperature increase of like overall temperature increase estimated is 2 degrees Celsius to 5 degrees Celsius? That is what we think is climate sensitivity. Climate sensitivity means if we double CO2 or double the double the CO2, how much temperature increase will be there? Because so we have not seen 2 degree or 4 degrees Celsius. We have already produced that effect 3 watt per meter square, because it is believed that we have cancelled some of that effect. Okay, some of that effect has been cancelled by what is called, so these are some minor contributions as well. So for example, nitrates actually cool earth a little bit. Okay, then there is carbon monoxide, carbon dioxide, etc. But this is what is called aerosols. Okay, so if you look at the atmosphere, now it looks less clear. Okay, so for example, especially if you go to northern Indian, Delhi and all, there is so much smoke and haze. So because of increased pollution, first of all, we have added what is called aerosols to the atmosphere, especially your sulfur dioxide, SO2. Now sulfur dioxide is a reflective, okay, component of the atmosphere. So it reflects radiation. So if it reflects radiation, it will produce a cooling effect. Okay, so we have not seen as much warming as we would expect, okay, from adding greenhouse gases, because of these additional components, which is called aerosols. Okay, so aerosols also cause more cloud production. Okay, aerosols also cause more cloud production. So how those clouds affect, as I said, like with clouds there is huge uncertainty in the models. Okay, they cannot model them pretty good. Aerosols and etc. Now we say that earth has not warmed as much as we predicted because of some cancelling by these aerosols. But the effect of aerosols is, we don't understand it very well. It is uncertain. Its effect could actually be, they could also be warming the earth. So this is the basically expected value of what is the effect of aerosols. So it is believed that they will be slightly cooling, but you see this bar is the uncertainty. Okay, so there is some, it could also be that they are not cooling but they are warming. Okay, and this is cloud adjustment. So overall, if we add all these up together, okay, so we have basically instead of 3, it is 2.29, okay, radiative forcing relative to 1750 watt per meter square, okay, which we will receive at the surface after reflection and everything else. 17, sorry, relative to 70, it was not 750. Okay, it is 1750 is much too high. It is year 1750. So compared to 1750, we have increased forcing by 2.29, and that is also estimated. There is uncertainty in that. It could be 3, it could also be more than 3 if we take these uncertainties into account, which has produced like increased temperature by roughly 1 degree Celsius. Okay, so that is where the climate sensitivity part comes into picture. Okay, which is effect of increasing concentration of CO2, making it double, and how much temperature will increase. Okay, so is from 2 degrees Celsius to roughly 4.5 degrees Celsius. and this is where like most debate is, okay, in climate science. Some people think like it is closer to this value, okay, some people think it is closer to this value. So if the sensitivity is closer to this value, okay, then it is a bigger problem. It is still a problem here, it is less of a problem. There are some actually on this side of the spectrum also that they say it is approximately 1 degree Celsius, and some say it could be 0.75 also, okay. So they are not considered mainstream, okay. This is the mainstream view. Okay, all right. So these are like some basic concepts on radiation and all, and then there are like effects of climate change and all. I will not go into those details right now because there is like a lot of uncertainty, a lot of garbage is also out there, okay. When you read news and everything, I mean climate change is basically affecting everything from domestic violence to the stock prices and everything. So those things are a bit of nonsense, okay. Even things like, for example, weather extremes, okay. There is, for example, Pakistan floods are like everywhere. You will see like they were caused because of climate change. It is very hard to pinpoint those to climate change. Disasters have been happening for always on that. There have been disasters, okay, and disasters will keep happening. So it is very difficult to pinpoint them to increasing CO2. That is what is increasing those climate extreme things like hurricanes, etc. If you look at the actual data, the hurricanes have not increased, intensity of hurricanes have not increased, okay. Some of the biggest hurricanes that you'll see, they happened around 1950s and all, okay. Those were like more active hurricane seasons. Or even if you go back even in past, okay, before that, there were more, for example, in 16th century, 17th century, there were more forest fires than you see currently, okay. Wildfires were more prevalent in those in those times. But it is like in media you will see a lot of basically headline making material which is not always based on science, okay. So of course it is a matter of concern, okay. It is kind of like an experiment we are running with with Earth, like adding CO2, more and more CO2 to the atmosphere. What effects will it produce? There is a lot of uncertainty in those, but there is a potential that it could produce very negative impacts, okay. Now what these 2 degrees Celsius could increase, so it could cause, for example, can you give some effects of what this global warming might produce? Okay, sea level rise, okay. Why will sea level rise? What will cause sea level to rise?
Sir, water in oceans may expand a little.
Expansion of water as it warms. Okay, so currently it is the main contributor to sea level rise, okay. Currently this is the main contributor. Another way, what else will cause sea level rise?
Continental ice melt.
Yes, very good. Continental caps melting. Please note that melting sea ice does not increase sea level. And sea level has been rising, like maybe there has been some acceleration in the past few decades, but sea level has been rising ever since we came out of the last ice age, okay. At the last ice age, in fact, Asia and North America, they were connected by this land bridge, the Bering, what we see Bering Sea right now between Alaska and Russia, okay. There is a small sea in between that was not present. The sea levels were lower, so there was a land bridge which connected North America and Russia, basically Asia, okay. So sea level rise, what else do you think can happen? Basically melting ice caps and all those things, okay. There are like other things also, okay. So for example, weather extremes will become more common and all, okay. I would still say there is like decent uncertainty in those things, okay. But from exam point of view, you can like if question comes, this is like mainstream view that forest fires will become more prevalent, drought may become, extreme rainfall events will become more common. Okay, so all those things are there. Okay, but it's all like predicting in the future. Okay, nobody has yet shown that that is actually something that is happening. Okay, sea level rise is definitely that's going to happen if there is any sort of warming. Okay, so it will not go in the other direction. All right, any questions, doubts?
Sir, is ocean acidification also directly related to this temperature increase?
Ocean acidification is more related to increasing CO2 concentration. Okay, yeah, for exam you can learn like ocean acidification is a problem. It is not too much of a problem really. Okay, so increasing CO2 concentration. Okay, so what is pH of seawater? Do you know approximately? I think it is 8.2. Maybe it may become 8.1. Okay, if we add like a lot of CO2. Okay, so ocean acidification is again a news capturing highlight, but it's like ocean will not become acidic. Ocean is already basic. Okay, maybe it will become slightly less basic, but it is mainly due to increasing CO2 concentration, because CO2 can dissolve in water to form what?
Carbonic acid.
Carbonic acid. Okay, and like with increasing temperature, amount of CO2 that you can dissolve in water. Okay, that is another effect. Okay, one of the feedbacks that you can write down. Okay, so cold water versus warm water. Okay, in which type of water do you think there is more dissolution of gases? Okay. Okay, so as you add, okay, so basically as you add CO2, like atmosphere, there is increasing CO2. Okay, so basically what will happen is more CO2 will want to dissolve in water. Okay, so more carbonic acid will be there, but if it warms the planet, okay, solubility of CO2 decreases. Okay, solubility of CO2 decreases, and that decrease in solubility basically will call what is called degassing. Okay, so that will decrease CO2 concentration in water. So increasing atmospheric CO2 is trying to increase CO2 in water, but warm temperature is trying to decrease CO2 in water. Okay, so some of it will be offset, is kind of like a negative feedback for if you look for CO2 present in water. Okay, so ocean acidification again, it is more like a news material kind of topic. Okay, overall, as you can see, like on Earth, life has persisted, like shelled organisms, etc. Maybe like they were not evolved in the current environment, but in Paleocene and all, you see like it was 2000 parts per million. If you go back further in time, like when life evolved in Cambrian, it was I think 4000 parts per million, like 10 times higher CO2 in atmosphere than now, and the life was able to actually evolve. Like right now, it has to sustain. The only problem is like, yeah, right, like life today is more adapted to current conditions. Okay, if you change the conditions and life cannot adapt fast enough, so then there will be a problem. Okay, there will be extinction of some species if humans cannot adapt fast enough. So that is a problem. But overall, like throughout these kind of like big changes, life has persisted on Earth. Okay, but like yeah, you can expect some ocean acidification with increasing CO2, but it is not like an existential threat kind of a problem. Right? Any other questions?
Sir, I have a question regarding calculation of coordination number.
I'll take those in the next class. I'll take like one more live class. Okay. Currently, because this is also live on YouTube. Okay, stream. You have you shared that question in the Telegram group?
I am sharing, sir.
Okay. Okay, I'll respond in there only. Okay, or like we'll take that in the next class. Okay.
Yes, sir.